Today I am going to teach you introduction to statistical mechanics from thermodynamical approach. A system, be it a system of molecules, a system of magnetic moments, or a system of electrons or protons or spins, is described by a dynamical model, right? So this model possesses two major components. The first one is time evolution of the system that follows the laws of classical mechanics, typically Newtonian, or the laws of relativistic mechanics by Einstein, or the laws of quantum mechanics, Schrödinger. And the second one is the driving force behind this evolution, either electromagnetic or gravitational, etc. The degrees of freedom that we conventionally use DOF of the constituent atoms or molecules are assumed to be stable and perhaps essential for the coexistence of statistics and the mechanics of a given physical system. For example, the ideal gas is simply described by the coordinates and momenta of total 6n variables of its molecules. We have already gone through classical mechanics in the course of mathematical physics 3, where a 3n coupled second order differential equation is to be solved to its microscopic evolution governed by the Newtonian mechanics. So in particular experiments, we does not bother about detailed evolution instead of averages over long time or large spatial regions, which means the duration of the measurements, or we conventionally call it observables, that means any measurable quantity, are very long compared to the times during which the system changes its microscopic state. I will come into details what is macroscopic, what is microscopic state. For instance, the microscopic time in a gas will be the time between successive collisions. The mean free time, or we conventionally call it the characteristic time, after which the particles change their velocities. The system may change its state for various reasons, that is, forces like electric or magnetic field or any external force, or because of the effects of the surroundings, that is, system in contact with a heat reservoir, etc. 1 gram mole of a gas contains Na, we know, Avogadro number, 10 to the 23 number of molecules, and it is ridiculous to apply laws of mechanics to such a physical system containing large number of particles, particularly that of electrons. Statistical mechanics is a solution maker, as the statistical predictions agrees well when the frequency is higher or larger in magnitude. Before the discovery of quantum mechanics, Maxwell, Boltzmann, Gibbs applied statistical methods, making the use of classical physics known as classical statistics or Maxwell-Boltzmann statistics, which successfully explained the phenomena like temperature, pressure, energy, etc., but failed to explain blackbody radiation, specific heat at low temperature, etc. However, experimental observations of macroscopic behavior of physical systems through the work of Carnot, Joule, Clausius and Kelvin, thermodynamics was established, right? So statistical mechanics is the indispensable tools for studying physical properties of matter in bulk. While most branches of physics, that is classical mechanics, atomic physics, quantum mechanics, nuclear physics, all deals with one or two or a few dozen of particles, statistical mechanics deals with typically about a mole of particles at an instant. Statistical mechanics deals with two important subject areas to describe systems in a broad sense. One is mechanics and another is statistics. Mechanics is the branch of physics we all know, which deals with action of forces on bodies, comprising of kinetics, statistics, and kinematics. So in a more general sense, this branch describes the behavior of a system of molecules, a system of magnetic moments, or a system of electrons, protons, or spins by a dynamical model that I have already discussed. So given the positions and velocities of all the particles now, the underlying theories allow us to find out what they will be at some later time. This problem was not been completely solved for three gravitating bodies. Clearly, we will get nowhere asking the same question for 6 times 10 to the 23 bodies. Examples include the air in a balloon, or the water in a lake, the electrons in a chunk of metal, and the photons or the electromagnetic wave packets given off by the sun. Anything big enough to see with your eyes or even with a conventional microscope has enough particles in it to qualify it as a subject of thermal physics. Consider a chunk of metal, for example, containing perhaps 10 to the 23 ions and 10 to the 23 conduction electrons. We cannot possibly follow every detail of the motions of all these particles, nor would we want to if we could. So instead, in thermal physics, we assume that the particles just jostle about randomly, and we use the laws of probability to predict how the chunk of metal as a whole ought to behave. Alternatively, we can measure the bulk properties of the metal, that is stiffness, conductivity, heat capacity, magnetization, and so on, and from these we can infer something about the particles it is made of. So some of the properties of bulk matter do not really depend on the microscopic details of the atomic physics. Heat always flows spontaneously from a hot object to a cold one, we all know, and never the other way. Liquids always boil more readily at a lower temperature. The maximum possible efficiency of an engine working over a given temperature range is the same whether the engine uses steam or air or anything else as its working substance. But to understand matter in greater detail, we must also take into account both the quantum behavior of atoms and the laws of statistics that make the connection between one atom and 10 to the 23. Then we cannot only predict the properties of metals and other materials, but also explain why the principles of thermodynamics are or what they are, why heat flows from a hot body to a cold one, or for example, this underlying explanation of thermodynamics and the many applications that come along with it comprise a subject called statistical mechanics. But in fact, a solution of the time development problem for a mole of water molecules would be useless even if it could be obtained. Who cares where each molecule is located? No experiment will ever be able to find out. To make progress, we have to ask different questions like how does the pressure change with volume? How does the temperature change upon adding particles? What is the mean distance between atoms, or what is the probability for finding two atoms separated by a given distance? Thus, the challenge of statistical mechanics is twofold. Firstly, to ask different questions and then to find the answers. So statistical mechanics make predictions about the macroscopic properties of a system using information only about the microscopic nature of the system, which is determined by calculations using mechanical theories or models. As for example, the ideal gas is described with the coordinates of momenta of total 6n variables of molecules, n being the number of molecules and 3n coupled second order differential equation that I have mentioned. Now, in the plural sense, the word implies a set of collection of facts numerically expressed, enumerated or estimated according to reasonable standard of accuracy, collected in a synthetic manner for a specific purpose and placed in relation to each other. These are also collectively known as data. In the singular sense, it refers to the subject of scientific activity which deals with the theories and the methods of collection, presentation, and analysis of quantitative data for the use of such data for interpretation in decision making. But how much statistics is used in statistical mechanics? Now, a lot really, not a lot really. It uses a lot of probability. Therefore, one need not use all these wondrous funny named tricks, huge tables and weird functions that are learnt in statistics classes. One is more likely to see these in any science that does statistical measurements. Really, the name is a bit of a misnomer, except in the connection of probability and statistics, which is really kind of vague and basic. So, in thermodynamics, concept of fundamental equations plays a prominent role. From one such equation, many profound predictions follow in a completely general fashion. However, thermodynamics itself does not predict the explicit form of this function. Instead, the fundamental equation must be determined empirically for each system of our interest. Being a science built on a set of macroscopic observations, thermodynamics does not offer any systematic way of incorporating molecular level information either. Thus, an approach based solely on thermodynamics is not sufficient if we hope to achieve desired materials properties through manipulation of nanoscale features or molecular level architecture of materials. It is in this context that the method of statistical mechanics becomes important for us. Equilibrium statistical mechanics provides a general framework for constructing the fundamental equation from a molecular level description of the system of interest. It can also provide a wealth of molecular level insights that is otherwise inaccessible even experimentally. So, thermodynamics deals with the macroscopic properties of matter. Thermodynamics is not dependent on the fundamental nature of matter. That is, thermodynamics is a valid whether matter is made up of atoms or molecules or whether matter is made up of some kind of continuum fabric. Quantum mechanics deals with the behavior of matter on the microscopic scale. In quantum mechanics, we calculate the energy and behavior of a few atoms or small molecules. Most calculations are performed at T is equal to 0 Kelvin. We cannot get the macroscopic properties such as the equation of state, etc. from quantum mechanics. Statistical mechanics is a bridge between quantum mechanics and thermodynamics. We seek to use statistical mechanics to compute macroscopic properties from the quantum mechanical information about the atoms and the molecules of interest. So, quantum mechanics is tunneled by the macroscopic thermodynamic properties through the bridge named statistical mechanics. Statistical mechanics is the theory of the physical behavior of macroscopic systems starting from knowledge of the microscopic forces between the constituent particles. A model of a physical system is a caricature of the system obtained by extracting only the essential features of the phenomena to be studied so that it becomes manageable for mathematical investigations.